Welcome everyone to the second of the Paul Bernays lectures of Kevin Buzzard. And so we will talk today about mathematics and the computer from the point of view of an interactive problem solver. Please.
All right, hello. Thank you for coming back. So this is lecture 2 of 3, and in this one I'm going to show you my favorite computer game. So in the last lecture, for those of you that came, I gave some examples of novel uses of neural networks in research mathematics, and I think we'll see more in the future. But the thing is, in these examples, typically the situation was you had some table of sort of data, and you wanted the network to analyze the table and tell you things about it that you didn't know before. And that's what some of mathematics looks like, but some of mathematics you can't tabulate. And so maybe sort of neural networks, neural networks in the way I presented them yesterday are not of any use at all. And so in this lecture, I'm going to show you a piece of software that's sort of so incredible that it could sort of interact with all of mathematics. It doesn't have to be the kind of mathematics that you can reduce to, a finite dimensional input to a neural network or whatever. So this software is called an interactive theorem prover, and what they do is they turn the problem of proving a mathematical theorem into a computer puzzle game. And I mean, the best way to show you what they look like is just by showing you one. So let's do this. Great. Oh, there we are. Let's get rid of that. See, I'm very well prepared. It's just suddenly occurred to me I might have left something on. No, I think I'm okay. So this is a computer program, and the first line of the program imports a bunch of without that line, the system would be. Without that first line, the system would know logic, but wouldn't know any mathematics at all. And then we import a large amount of stuff, and then it's not clear, but after that import, the system now knows all about things like groups and rings and fields. So there we go. So now suddenly this thing has become, knowledgeable about basic mathematical objects. And this second line here says, let x, y, and z be sets, and let f and g be functions. And it doesn't say sets, it says types, and that's because this is a foundational issue. So I guess these are the Bernays lectures, so maybe I should say something about foundations of mathematics. Somehow, set theory won for some random reason, but logicians pointed out over 100 years ago that what mathematicians were doing, that it was possible to turn what mathematicians were doing into some kind of logical system where there were axioms and the theorems could all be deduced from the axioms. So I guess Pythagoras somehow knew that thousands of years ago, but then mathematics got a whole lot more complicated. And then the logicians came along and said, even though it's much more complicated and we have this stuff like topology and what Riemann is doing and what Euler is doing, at the end of the day, everything can still be reduced down to axioms. And the big problem with somehow to start off how this works is what you realize is that sometimes mathematicians talk about concrete things like the real numbers or the natural numbers or the integers mod 10 or whatever. But sometimes they want to talk about abstract things, right? This is just beginning to happen, in the 1800s and early 1900s. People wanted to talk about things like the concept of a group. And a group, an abstract, not like, see, Galois was thinking about concrete groups, like permutation groups of roots of, polynomials and things like this, or SL2 of Z, or concrete groups. But then there's this, after a while you realize that there's this common abstraction, the concept of an abstract group. And an abstract group is just a collection of things that we can call elements, and the collection itself is like nowadays we say it's a set. So an abstract group is a set. And the great thing about set theory, in fact, is not just abstract groups that are sets. In set theory, everything is a set. And even elements of sets are sets as well. So if you kind of take a group and then you take the identity element, that's not really a set, right? That's just an element. But in set theory, you can take that identity element and strictly speaking, it will turn out to be another set. And you could look at the elements of that if you wanted. And then you wouldn't be doing mathematics anymore because you're not supposed to start opening up elements of groups. So type theory is another foundation of mathematics. And in type theory, you can't do. In type theory, in set theory, there's one thing, the set. And in type theory, there's two things. There's types and there's terms. And types are the collections of stuff, and terms are the elements. But you can't take a term. A term isn't a type, whereas an element of a set is a set. So that's the only difference, really, between, as far as we're concerned, at least in this lecture, between set theory and type theory. So x, y, and z are sets, but I've called them types. And f is a function from x to y, and g is a function from y to z. And now I've got to prove I'm going to prove to you. I want to show to you that proving a theorem is the same as playing a computer game. So let's put that over there. Great. And so the exciting theorem I decided to prove was that the composite of two surjective functions is surjective. So x, y, and z are sets. F and g are functions. And then the claim is, if we have the hypothesis that f is surjective and the hypothesis that g is surjective, then after this colon we have the conclusion, and the conclusion is that g composed with f is surjective. And if I asked you to prove this on pencil and paper, I suspect that essentially all of you will be able to write down a proof on paper. But what I'm going to show to you is that actually, if you know, so here on the left, I'm going to be typing stuff in a computer programming language that might be difficult to understand. But here on the right, we have all the hypotheses, and that stuff is the current state of the brain of the theorem prover. And so currently the theorem prover knows that x, y, and z are sets, that f and g are functions, that f is surjective and g is surjective, and then there's this funny logic symbol here, this sideways t, and the sideways t just means, as far as we're concerned, everything above it is a hypothesis, and everything to the right of it is what we're trying to prove. So let's try and prove it. So I guess the first thing we need to do is work out what being surjective means. So we could perhaps do unfold surjective everywhere. And then, you've seen the brain changed, right? So that's a line in a programming language, and now the computer thinks something different. The computer doesn't think that f is surjective, it thinks that for all b there exists an a such that f of a is b. And similarly, it thinks that for all b there exists an a such that g of a is b. And that's like a lousy, I would never do that if I was teaching, right? I would never use a and b to mean, I would use y for the element of y, and I would use z for the element of, little z for the element of z. So you can kind of see already this is kind of confusing if you're a learner. But logically speaking, it doesn't matter that all these variables are called b. And what have we got to prove? So we've got to prove that for all elements of z, there exists an a, which will be an element of x, so that the g of f of a is equal to. So we've got to prove something for all elements of z. So let's take an arbitrary element of z there. And so now we've got an exciting new thing here. We've got that element of z there. And I've got to prove that there exists an element of x. It's not obvious that this a is an element of x, but if I hover over it, there we go. It says there's some x mentioned somewhere. So the software is complicated, but once you know how to use it, you realize you're just doing mathematics.
How did it know that z is in z?
Oh, it knew it's I get this question a lot. It knows, at the beginning, it knows we're trying to prove that this function is surjective, g composed with f. And it can work out that g composed with f goes from x to z, because it knows that f goes from x to y and g goes from y to z. So it knows that this function goes from x to z. And so it knows that we've got to prove that every element of z comes from x. So where are we going to get this element of x from? Now I've got to work out how to prove the theorem. Yeah, okay. So we've got g from y to z is surjective, and we've got an element of z, so let's use the hypothesis of surjectivity of g to get an element of y, and I guess I would do that with, I would do specialize hg at z. That should do it. There we go. And now we know that there exists an element of y such that g of y is... You see, they're all called a. Isn't that terrible? There's nothing I can do about it. Computer scientists don't care. Look, I could do change. There exists a y in y such that g of y is z at hg. Can I do that? There we go. Look, now it's now I've got a y. And now, but this don't actually have a y. I've got a z, right? I've got that orange letter z, so I've clearly got a z. I don't actually have the y. I just have a theorem that says that there exists a y, so we need to get the y now. So let's get that y. Our case is y. No. Our case is, what was it, hg, with a y and hy. How about that? So there we go. And now, so now we have an element of y, and also we have the hypothesis that g of that element of y is z. So now I use surjectivity of f. So now we can do the same thing. What can we do? We can specialize hf at y, and now, and then we can take that apart. Our case is hf with x, hx. Oh, pointy brackets. X, oh dear. Pointy brackets, wrong pointy bracket. There it is, x, hx. So now we have an element of x. So this looks good now, right? We have an element of x. So f of x is y, and g of y is z. So that's going to work. So let's use x there. And now, I don't know. So now I guess, I mean, as far as I'm concerned, we're done. But the computer's just like, yeah, go on, like put everything together. All right. I know that z is equal to g of y. So let's, how about we do this? Let's rewrite, let's do this. Let's rewrite hy. That should change the z's. There we go. I've changed, that line there changed z to g of y, and then I'll do the same thing here. Rewrite hx. There, and now I've changed, so now this is looking really good, because now I've got to prove that g composed with f of x equals g of f of x, but that's just the definition of function composition. And so this goal here says g of f of x equals g of f of x, and so this is true by reflexivity of equality, right? And reflexivity of equality is called REFL, and there we go. And now we proved it, and so now there's no goals left. So that's me taking a very long time proving an incredibly simple theorem. And now you can kind of say, okay, that's great. I mean, how far does it go? And in some sense, that's what this talks about. So that was an interactive theorem prover. That interactive theorem prover was called Lean. There's several other serious interactive theorem provers that exist. Lean is a relatively new one. It was developed by Leo DeMara when he worked at Microsoft Research. He's just left Microsoft and gone to Amazon Web Services now because they're interested in using this stuff to do, AI things that I don't really understand. So it's not entirely clear now that Microsoft is supporting Lean anymore, but there's a new organization which is supporting Lean instead, called the Lean Focused Research Organization. And this is being funded by Sloan and Simons and people like that. So mathematicians, like big math funding agencies, are now getting involved, which as far as I'm concerned is quite exciting. So Lean has got a mathematics. I wasn't just using bare Lean by itself. I was using Lean's mathematics library. Things like the definition of a surjective function is not in Lean itself. That's something that a mathematician has decided was a relevant mathematical concept. So Lean's got a mathematics library called MathLib, and There are several other interactive theorem provers that exist. I mean, there's many other interactive theorem provers that exist. But those, here's a couple, I mean, Koch and Isabel Holl are two which are also being used to do sort of serious mathematics. So I mentioned those two, and they also have serious mathematics. There are other interactive theorem provers that people use to do completely different things, like verify that code has got no bugs or something. And so those interactive theorem provers, they're proving theorems, but they're not proving mathematical, they're proving theorems about computer programs, for example. And those other theorem provers might not have a big mathematics library at all. So those are three, and lean is the one that I use because I chose one randomly. So what's the point of an interactive theorem prover? So we can teach them the axioms of mathematics, and then they offer us a completely new way of doing mathematics. And like, we have existed as mathematicians for centuries, and the big question really that I want to talk about in this lecture is, what's the point? What is this software giving us that we didn't have already? And this is a very hard question, and I think for many, many years the answer was we can't see a point. This software, in fact, has existed for nigh on 50 years, and 5 years ago, essentially no mathematician had ever heard of it. But they are quite popular in computer science departments. They're being used by computer scientists all over the world to teach computer science students sort of basic logical arguments. And this is really, in some sense, this was part of the, I mean, there's lots of problems, but this is part of the problem in that these are all designed by computer scientists, and they're being used by computer scientists. And so typically to install one, you have to use the command line, which already is a bit of a shock to a lot of mathematicians. And the documentation is also kind of unreadable in the sense that it's, the examples are all weird things about reversing lists instead of being questions about finite groups. That the examples are wrong, and everything is wrong. This is really not an area it's doing mathematics, but it was not an area designed to be easy for a mathematician to use. So this was the problem I faced in 2017 when I entered the area, was that there was a lot of barriers to even understanding what was going on. And I should say that they were solved because there's a chat. There's like a lean chat room on the internet. And whenever I had a question, I would ask this question, and it would get answered essentially instantly by a computer scientist. So that was how I learned lean, by just asking, by spamming the lean chat room with completely stupid questions. But now we're 6 years on from that, and one thing we're trying to do in the lean community is try to fix that issue. And so now there is documentation which is suitable for mathematicians. In particular, this book, Mathematics in Lean, is an introduction to how one, it's got sections on linear, vector spaces, group theory, basic number theory, this sort of thing. So this is somehow documentation that mathematicians can actually understand. So if you want to learn how to use lean, then I would point you to this Mathematics in Lean textbook. Okay, so what's the point? Well, I guess, here's a great idea, right? Maybe we could use this software to teach a first course in mathematical proof. Because, there's one of those in every maths department. So this is a very old idea, essentially as old as the software. And it's an absolutely disastrous idea, it turns out. And I didn't realize this at the time in 2017 when I independently had this idea. But when I started talking to mathematics education specialists, they started telling me all the reasons why this was a terrible idea. And it can be summarized in the following observation. Right, now I'll tell you why. Sorry, we don't get the observation yet. I'll tell you why it doesn't work. It doesn't work because somebody decides it's a great idea, and they introduce this complicated software into their. They learn how to use the software. They introduce it into the class. Some of the students love it. Some of the students hate it. Some of the students can never get it to work. And the professor teaches the software for a few years, and some of the students complain, and some of the students just get used to how it works and they learn it. And then after a few years, they decide it's time for someone else to teach the Introduction to Proof course. And so then the new professor can't use the software at all and can't be bothered to learn how to use it because what advantage is actually giving you? And so the new professor goes back to the old way, and then this software that got developed, just sort of stagnates and dies. Because people write bespoke software to teach basic proofs to undergraduates, and this software typically never catches on. And really, maybe the reason it doesn't catch on is because we've got a system. Like you write stuff on the blackboard. It works. It's worked for centuries. So in completely ignorant of all these problems, in 2017, I thought, I'm very interested in teaching. I thought, this is going to be great. I'm going to start using this. Because you just saw, right? The system is really keeping track of everything, okay? It's like, I know it was calling too many variables A and B, but it's sort of keeping track of everything. It was explaining to you what a basic proof was. So what I expected to happen was that these weak students that just don't get logic at all, because I'm teaching these people, they've come straight from school, and at school they've seen essentially no proof, right? At school they've learned how to do calculations. And so I've got this room full of people that have never really seen a proof before, and some of them don't get, by the time you've got to equivalence relations, they're completely lost somehow. But as you can imagine, this system does equivalence relations quite well. It completely keeps track of everything, and you have access to reflexivity, symmetry, and transitivity, and you can just prove that equivalence relations are the same as partitions, and it comes out very nicely. So that was my naive idea, was that people that didn't really ever get this whole idea of a logical argument, they would see it just being, it's a game, it's a rule, it's like chess, and that was the idea. So unfortunately, the software is incredibly hard to use, and if you're the kind of person that is struggling to understand equivalence relations, then unfortunately, the last thing you want is some crazy person at the front telling you that you need to learn how to use this complicated software because it's definitely going to make your life better. I mean, it's not going to make your life better. It's going to make your life better. So I discovered this at the end of week 1, basically. So I started teaching this course, and I also started a lean club. And the idea is that the strong students don't need to come, but the weak students will come along. This was Thursday evenings. The weak students would come along, and they would, I would help them install the software, and I would teach them how to use I'd teach them the language, and at the end of the day, they would all be brilliant at questions on equivalence relations. So that was the idea. So no weak students show up at all, because I'd made it clear it wasn't going to be in the exam, right? It was an optional part of the course. But all that happened was these super strong students that knew all the course back to front already, because they'd downloaded last year's course notes when they were still at school and had gone through them over the holidays. And they were doing these courses, but my course was the only course that had anything that was sort of difficult in it. And so these strong students started showing up, and then I realized I had to find something for them to do. I was expecting to be teaching them equivalence relations, but this is week 1. Equivalence relations are week 9. But these people that showed up, they all know what an equivalence relation is already. And so I had to think of something to do with them. And what did we have? We've got this new theorem prover lean. And this is the kind of things it had in the library. It had definitions of groups, rings, and fields, metric spaces and topological spaces, topological groups, because computer science, a computer scientist had heard that there was such a thing. So we just sort of typed the definition in off Wikipedia. And they had sets, except they were called types. They had finite sets, functions, partial orders, equivalence relations. Great, I'm teaching them naturals, integers, rationals, and they're just the month before they just defined the real numbers. So that was where we were. And then the things I was planning on teaching these undergraduates. This was the introduction to proof course, and some of these words are the same, right? Sets and functions and equivalence relations, that's great. And some of these things are different, right? We've got complex numbers. So e to the I theta is cos theta plus I sine theta. They learn this at school. It's one of the last things they learn at school. So we do sort of basic revision of e to the I theta is cos theta plus I sine theta. And also we do some basic counting, because counting is, just combinatorial questions about how many things are there with this property. So there were some things that were there on this list that are not in lean, but it's all right because we can just make them, right? It's going to be easy. So we're doing all this stuff because this is easy mathematics, therefore it's going to be easy to do in a theorem prover. So this was totally wrong. My whole idea about what was easy and difficult in mathematics was turned on its head in this period. So for example, e to the I theta is cos theta plus I sine theta. Well, we didn't have e to the I theta. We didn't have I. we didn't have, they'd only just made the real numbers. I made the complex numbers in Lean's maths lab. I defined a complex number to be a pair of real numbers. That was my first contribution to the maths library. But now to prove that e to the I theta is cos theta plus I sine theta, you need to define cosine and sine as infinite sums. You need to develop the theory of limits of sequences and limits of sums. And also this involves a rearrangement, right? You've got to e to the I, when you expand everything out, so you've got to prove that these things don't just converge, they converge absolutely. And if you converge absolutely, you can rearrange the order of the summation. Things work fine. And all of this stuff, that's not what I'm supposed to be teaching. That's in the next course. That was the course after my course, they start learning analysis formally. So I felt that it was sort of not really the kind of thing. So the problem sheets involving e to the I theta, I just had to skip them. That was there was going to be no e to the I theta in my course. Well, there was, but there was going to be no. I wasn't going to use Lean in those lectures. So counting sounds very easy, but counting is also incredibly difficult. So if x is a finite set, then what's the size of x? It's like, well, you just count how many things there are, right? You don't have to define for the students what the size of x is. So isn't this clever? So there we go. So there's a set with 3 elements. And it's obviously got 3 elements because I can count them. But this is a picture, right? And that's exactly what you can't do in Lean. You can't do any pictures. And so we're going to have to come up with a definition. So we could maybe define a set to be finite if there exists some n such that it bijects with 1 up to n. That would be good, right? And we could define the cardinality of that set to be n, except the problem is, how do we know for sure that if a set bijects with 1 up to a, that it can't biject with 1 up to b if b is not equal to a, right? And obviously 1 up to a can't biject with 1 up to b because 1 up to a has got size a and 1 up to b has got size b, but that argument's circular because we're trying to define size, right? How do we know that a finite set's got exactly one size? So, now you've got to do something. We've got to sort of think, if there's a bijection between 1 up to a and 1 up to b, then we rearrange the bijection, so there's a bijection sending A to B, and then we remove A and B. We prove it by some kind of induction on. This is sort of a nightmare, right? And this even worse, right? What's the proof that the size of the product? What's the proof that the size of the product is the product of the sizes? Is this, right? You just draw a rect. There you go. That's a proof that if one set's got size 4 and another set's got size 3, then the product has got size 12. But the definition of multiplication in Lean is not count the rectangle, right? The definition of multiplication is some kind of recursive definition on the second variable. X times 0 is defined to be 0, and x times n plus 1 is defined to be x times n plus x. So proving that the size of the product is the product of the sizes is completely out of reach, right? Like no way are we going to get students doing that? So all the counting stuff was completely out the window as well. So there you go. That is not a proof of anything, right? That's a picture. That will do for the students, but it won't do for the theorem prover because that's the game we're playing now. So you had to really start renormalizing the way I was thinking about mathematics. You've got to reduce everything to the axioms, and pictures don't count. I should probably say, of course, the idea is you don't prove it, right? Somebody's proved it already for you. The fact that the product of the set, the size of the product is the product, is going to be in the library already. So there was me struggling in week 3 with this stuff, but by the time we got to the difficult stuff in week 9, the stuff that I thought was, quotes, difficult, this was really, really easy to do with the theorem prover, because equivalence relations are just defined by 3 axioms, and you make those 3 axioms, and that's it. Right? And then everything just sort of follows immediately from the axioms. So by the beginning, by a few weeks into the course, I'd now got this renormalized idea about what was easy and what was hard. And I've also got these super smart first years that want a Lean project. And so So I gave one of them a graduate text in commutative algebra and said, why don't you go and define localization of commutative rings? Because I knew that, in theory, that's supposed to be hard on paper, right? But I knew that actually it was going to be easy. This is just the kind of thing that the theorem proof is really good at. Everything, because a ring is just a list of axioms, and this stuff here is just a construction and an axiom and a basic argument, and the basic, all you ever use in the basic argument is you're just constantly applying the axioms. So I knew this would be easy, and 2 weeks later this student came back and they'd done it. So, they're supposed to be going to my course and learning about binomial coefficients, but on my club on Thursday evenings, I'm teaching them about localizations of commutative rings. So they have it, and they wanted another project. So I thought, okay, well, let's define schemes. Because if we can do localization, what do you need to make it? Scheme is this something in algebraic geometry. You need topological spaces, and you need rings, and you need localizations. And that's pretty much all you need. So I thought, if localization is easy, as I suspected it would be, and it turned out to be, so easy a first year could do it, right? Then schemes should be easy as well. So by the end of my introduction to proof, this was not the plan at all, but by the end of my course, me and 2 first-year undergraduates, we got a working definition of scheme in an interactive theorem proof. And I hadn't taught anybody about equivalence relations at all, because the weak students were just doing things the old way, and the strong students knew that stuff already. So I proudly announced on the Lean chat room that we'd defined schemes, and the computer scientists just looked at this and was like, what? It's just a definition of a thing. Like, what is the point of this thing? Like, normally when you make a definition like a ring, you then make lots of examples of rings. So you've just defined schemes, but like, where's the application? Where's the theorem that isn't about schemes that you can prove using schemes? There, that would be. And I'm just going, but like, schemes are fundamental objects in math. You can't prove Fermat's last theorem. There's a good answer. You can't prove Fermat's last theorem unless you've got schemes. And they're like, yeah, but there's not a good answer because you haven't proved Fermat's last theorem. So they were just like, whatever is, and I'm just like absolutely adamant that schemes are fundamental mathematical objects, and they're just like, I've never heard of it, and I don't see the point. So I then started going around the department telling algebraic geometers that I'd just taught a computer to understand the phrase let X be a scheme. I was absolutely convinced that this was very exciting. And furthermore, I'd done it with 2 undergraduates. And Paolo Cascini in algebraic geometry at Imperial said, like, I knew our scheme was 20 years ago, Kevin. So there we go. That was where we were in Christmas 2017. So for the computer scientists, I tried this argument that there were fundamental objects in mathematics, but this didn't work. And so I proved a theorem. I proved that affine schemes were schemes. And if you know the definition of a scheme, you'll realize that this is not a particularly big deal. Right? This is it's true by definition. And a scheme is defined to be affine schemes glued together. So we proved that affine schemes were schemes, and given a ring, you can make an affine scheme. So I was like, great, now I've got infinitely many schemes, because we've got polynomial rings in arbitrarily many variables. So I've made you infinitely many schemes. So that applicated them, and they were like, okay, now this is great. Now we understand it, so you should publish it. It was just supposed to be a sort of stupid undergraduate project, right? This was just some random thing I was sort of doing as a hobby with these undergraduates that were sort of paying attention to this thing that I got completely obsessed with. Because I was just doing it all the time, right? I was, really addicted to this computer game. I was trying to experiment with all kinds of mathematics to see what was easy and what was hard. So they're telling me I should publish like this joint work with 2 first-year undergraduates. So I said, well, okay, but at least we should do some kind of survey and look at how it's done in all the other theorem proofs, because Lean was quite new back at that time. So it turns out no one's ever done anything like this before. And this is why they said I should publish it, because it's all being used by computer scientists, and on the whole, computer scientists don't have a clue what a scheme is. So we were breaking new ground completely accidentally, and this actually did surprise me, because I knew that Vladimir Voivodsky, who got a Fields Medal for doing algebraic geometry, also had been working in that area. He'd just died. It's one of my biggest regrets in some sense. I just got like 2 months after I started playing with Lean, Voivodsky died. And so I never got to ask him why he'd never defined schemes. I still don't. I think basically he'd lost interest in algebraic geometry. I think he'd become a constructivist and had lost interest in algebraic geometry. He got interested in foundations of mathematics. I suspect that would have been the answer. So now I've just got to placate Cassini. We'd formalised 5 pages of Grothendieck's EGA, and so there's still quite a lot left. And it wasn't entirely clear that first years were going to be the way I was going to get this done. I was going to need a lot of first years. So I needed another idea, and then in 2018, Schultz got the Fields Medal. And he got the Fields Medal, and constantly when people would talk about what he got it for, there was these perfectoid spaces. So they sound really complicated. I mean, it's a great name. They sort of sound very complicated, and the definition is complicated. But it wasn't just the fact that he made some complicated definition. He'd used perfectoid spaces to prove lots of theorems in commutative algebra and algebraic geometry. And I thought, well, I bet Paolo Cassini didn't know what perfectoid space was when they were a first-year graduate student. So I thought that's the way to crack the algebraic geometers, is just kind of try to do something that, because I knew what a perfectoid space, this was my area, so I knew the definition. But I thought he doesn't. So we just went for it. And in 2019, this project did actually take us like 9 months. In 2019, we defined perfectoid spaces in Lean. And I got invited to give the algebraic geometry seminar. So it was definite positive result. So there we go. So what is this software? I mean, it enables us to do mathematics in a completely new way, right? That's what the point is. And in fact, it's a really sort of rubbish new way, because I spent sort of 3 minutes proving that composite of surjective functions was surjective, whereas on the board I could have done it in 30 seconds. And as I pointed out already, this software has existed for decades, and we just didn't care, right? Because what is it giving us? We now have a new, slower way of proving that a composite of surjective functions is surjective. But I was just convinced at the time, I didn't have a good answer to this question in 2019, but I was just convinced that the software was cool and fun, and also it enabled me to collaborate with undergraduates as equals, which is something I found very exciting, because we were all learning. The software is very complex to learn, and the students would learn it quicker than me. After a while, these first years were teaching me how to use the software. And I found that a very enlightening and interesting experience, because when you're doing the p-adic Langlands philosophy, then the first years can't tell you anything. But here, they were teaching me as much as I was teaching them. But I just had this vague idea that we were digitizing mathematics, and that must represent some kind of progress. Just in the same way that, we digitized music. In the 1980s, I had all these vinyl, and then there was people were telling me that I should start buying CDs now. And I was thinking, what is the point of a CD? And the point somehow became clearer later. The point is not just that the point is that a CD represents digital music, and digital music can be stored and copied and, sent across the internet phenomenally quickly. And now we have things like Spotify, right? So digitizing things changes things. You can use them in new ways. And I'm going to digitize mathematics, and I'm not entirely sure what the consequences will be, but it just seems like progress in some way. So more recently, I've had to actually start facing the idea that I should try and work out what the point of all this is. So the software is mostly being used by computer scientists for decades. So here's a brief history of some milestones. By 2002, they'd managed to formalize the proof of the prime number theorem. The element, not the complex analysis, but complex numbers are hard. But the elementary, the Erdős Selberg proof had been formalized in Isabel. And so by 2002, we're only 100 years behind. By 10 years later, by 2012, they'd taken on a really big, we teach the undergraduates the prime number theorem, but the Phi-Thompson odd order theorem, this is like a 300-page textbook just full of lemmas about finite groups. And so this was formalized over a period of 6 years by a team of 12 computer scientists. And the four-color theorem as well, this is a computer-assisted proof. And so you could sort of prove that the computer program has got no bugs that was used in that I mean, it's a bit more complicated than that, but the four-color theorem and the odd-order theorem were proved. And those were both proved in like the 70s, so now we're only about 40 years behind. And then by 2017, when I started, Tom Hales had just announced that he'd formally checked his proof of the Kepler conjecture. The Kepler conjecture was another computer-assisted proof. Hales submitted his paper to the Annals, and the referee said, well, this relies on checking sort of 70,000 nonlinear inequalities on regions of R cubed. And we as referees are not capable of checking, you say you've checked that using a computer program, but we're not capable of verifying that that program has no bugs. And so Hales was incensed by this response from the Annals and said, all right, I'm going to check this proof in an interactive theorem prover. And he did it. And again, that was like 20 people and 12 years. Another, a gigantic project. But now we're only 15 years behind. But this isn't the right question. There's a number of years behind, because there's something else going on with these theorems. And what's going on with these theorems is that they're all about really simple objects. And this is the kind of things that people were doing at the time. Prime numbers, planar graphs, finite groups. These are very mathematically simple objects. And our perfectoid space work, we just proved some very simple theorems. We didn't prove any of Schulz's theorems. We just wrote down the definition. As I said, now we can state the theorems. That was our contribution. We weren't claiming that we'd done anything as profound as what these other people have been doing. These gigantic teams of 12 people that had taken seats. This was like me and two friends I've met on the internet doing a 9-month project. So we proved that the empty set was a perfectoid space. That was one of our theorems. So there you go. But we'd proved simple theorems about incredibly complicated mathematical objects. And this is why I think the computer scientists were excited, because we seem to be using the software in a new way. And as I say, whenever we got stuck, the computer scientists, this is a really nice, the lean online chat room is a beautiful sort of blend of mathematicians and computer scientists sort of finding common areas of interest and thinking about the same question in different ways. And yeah, it's a sort of nice place for synergy. But one consequence of the goal really was that now I was beginning to realize, like maybe not from a mathematics point of view, but from a computer science point of view, we've now got a very natural goal, because we now know that the software can handle complex theorems about simple objects and simple theorems about complex objects. So the question is, can we prove a complex theorem about complex objects? So there's a research target. And now the question is, you have to decide which theorem. But another consequence was that the way the internet works. We're like, oh look, perfectoid space isn't a theorem prover. This was a thing, and people just started appearing. Mathematicians started appearing in young mathematicians in particular started appearing in their droves because perfectoid spaces were trendy. Because Schultz just won a Fields Medal, and they showed up and were just like, can we do anything? We're like, oh yeah, there's plenty. We've got 1,500 pages of EGA to get through. So if you know some algebraic geometry, maybe we could start there. So that was great. And as a result, this mathematics library that we're building everything on top of, the mathematics library started growing. So at the beginning, it just had groups, rings, and fields, and a couple of other things. But now just let me give you some kind of overview of what's in this library. For commutative algebra is really good, right? You could anything you want really in commutative algebra, we can get. These are just examples of things which people have come along and done. But all of this stuff, this is sort of a dream to do. It's very easy to do commutative algebra, and Lie algebras as well, just the same thing. We have the statement. You have the statement of the classification theorem of complex simple Lie algebras, and somebody is working on the proof now. So. Give me a few months, give us a few months, we'll have a proof. Differential geometry, the perfectoid space things tended to pull in sort of arithmetic geometers and algebraic number theorists. So differential geometry we're slower at, and I don't know whether it's because it's harder. I mean, David suggested to me earlier today that maybe differential geometry is just harder to do from the axioms of mathematics. But I'm very pleased we've just got to the point where we could start taking tensor product of vector bundles. And Riemannian manifolds is not in the library yet, but I've seen a working definition. And again, de Rham cohomology is on the way. Group theory, yeah, we just sort of did the standard undergraduate stuff. I'm not entirely clear where group theory is going, because I just don't know enough about group theory. But I got some undergraduates to do Suloff's theorems. We did like basic definitions of nilpotent solvable group. If you know some cute theorems in group theory, then feel free to add them to our library. We've got Galois theory. There were some natural targets in Galois theory, insolvability of the quintic, and fundamental theorem of Galois theory. We have for finite extensions. We're on the way to getting it for infinite extensions, but we're not there yet. We've got categories. Category theory, another thing that you can just do, right? It's just made for this stuff. We have a huge amount of category theory stuff, because things like homological algebra. This is what we needed this for the project I'll talk about tomorrow. But so we have applications of category theory in commutative algebra now. Representation theory, again, it's not like I just suggest to people that, I'm not in charge of the library, it's a big open source project, but if people ask me, if people ask me for a project, then I say, I don't know, just do some undergraduate stuff. So we're just doing undergraduate representation theory. Topology, basic, undergraduate topology we have. Real analysis would be a basic, so undergraduate level real analysis. Hilbert spaces, Banach spaces, LP spaces. We have measure theory. It's just standard, we're basically covering an undergraduate curriculum. That's where we are now. Complex analysis. We don't have too much about compact Riemann surfaces. I think we should have more Riemann surface theorems. Very recently, we got meromorphic continuation of the zeta function, thanks to David Loeffler. And he's also stated the Riemann hypothesis. So now we can just make a level, we can make a level of this computer game that's basically impossible to solve, which is kind of funny. And there we go. There was a very smart undergraduate interested in probability theory, and I got them in touch with a PhD student that was an expert in martingales, and they've ended up formalizing some difficult theorems about martingales. In algebraic geometry, we just have, we started with schemes and now we've got a bunch of stuff. And we don't quite have sheaf cohomology yet, but we've only just got sheaves of modules. So there's some overview. Oh, there we go, number theory. P-adic numbers, we've had them for a while. That was kind of cute. And quadratic reciprocity. Gauss sums we got quite recently. So so now you have some kind of feeling to what's in the maths library. Okay. So at the beginning, I said I don't really, I just felt I thought it was a good idea doing this stuff, but I wasn't really clear why. What was the point of formalizing perfectoric spaces? But here's a slightly different question. Maybe, what's the point of formalizing mathematics, but what's the point of making a formalized library of undergraduate level mathematics? Because that's clearly what's happened, right? Let me again stress, I'm not the leader of the project in any way. It's an open source project. Anyone who wants to join in can come along and ask questions on the Lean chat, and people just contribute. I happen to be there at the beginning, but I'm not in charge of anything. The community is in charge. Nobody's in charge. It's one of the nice things about it. So what's the point of digitizing all of undergraduate level mathematics? And as I say, in some sense, there didn't have to be a point. It was just an open source project on the internet. And the way that open source projects on the internet work is that people come along and they contribute to them. And that was just what got contributed. So it's not entirely clear that there needs to be a point, but maybe it would be nice to find an application. That would be good. You'd be careful. I used to do the p-adic Langlands philosophy. So what's the point of that, right? You could take an aggressive. Somebody says, "What's the point of your work?" You say, "Well, what's the point of all of it, right?" Pure mathematics is, if it doesn't have an application, what's the point? And a lot of it doesn't have an application. But let's not think about it like that. Let's try and work out if there are any uses for a formalized undergraduate library. And so one natural thing is you could regard it as it's the new Bourbaki, right? It's a 21st century version of Bourbaki. And in fact, the way it's written is very similar to the Bourbaki style. So for example, one famous one famous thing about Bourbaki is that they had a big argument about integration. Should they do integration theory first, or should they set up the entire theory of topological vector spaces and Banach spaces, and then define a super general integral taking values in Banach spaces, and then deduce the basic Riemann integral theory from that? And that's what we do. That's what we do in Lean's maths library. We develop a huge amount of very general theory and very abstract integrals, and prove some sort of very general form of Stokes's theorem. And as a consequence of that, we deduce like the fundamental theorem of calculus for of one variable integral. It's all completely ridiculous, but that's somehow, because what's the point of developing one variable calculus? Because you've got to develop multivariable calculus at some point, and having the one variable theory doesn't really help. You don't prove things by induction on dimension mostly. So you may as well just set up the multivariable theory first and then deduce the one variable theory afterwards. So the whole thing is it's difficult to use the library for teaching. You can use the software for teaching, but the library is not written in a way, we're not proving the theorems in the same order as you see them in an undergraduate course. So this is really one of the key applications. Really, is that other people can make other projects where they're not contributing theorems to the library, but they can use all the theorems in the library. So they can make other projects that build on top of the library. And how far can we get? So I think this is sort of an interesting observation, is that actually, in particular in the area of additive combinatorics, we've got to the point where you can formalize modern results in real time. And that, from 5 years ago, this was a complete dream. We had a system that had the real numbers and the complex numbers, and then there was the boundary of modern research, which was a long way away. But in some areas of mathematics, and additive combinatorics is probably the best example, we're at the point where if a modern research paper comes out, then we can actually check that paper using the maths library. And let me give you some just case studies. In 2021, Thomas Bloom resolved an old conjecture about unit fractions by Erdős and Graham. And the proof uses things like sort of the circle method and clever accounting arguments. And 6 months, just under 6 months later, the author of the paper and Bhavik Mehta, a PhD student of Tim Gower's in Cambridge, they completely formalized the entire, not just the paper, but like all the relevant references, they formalized the entire thing right down to the axioms of mathematics. And they managed to finish the formalization before the referee's report. So they sort of knew that the paper had no errors in before the referee did. So that was one example from 2021, but we've got more examples since then. That wasn't just a one-off. Bhavik has now gone on. So a paper came out earlier this year giving new bounds on certain Ramsey numbers, and Bhavik has spent the summer formalizing this, and he's not quite there yet, but he's clearly going to get there. You can look at what percentage of the paper he's formalized, and he's not quite. I can't announce it. He's not quite there, but he's got the vast majority. He's got to do some funny things. He's got to prove things like log of 101 is bigger than sort of weird questions about numbers that you just check on a calculator. But you've actually got to give a formal proof of these things, and it's sort of slightly more subtle than you might think. Because you ask Liam what the square root of 2 is, and he's just like, well, it's just like the sup of all the rational numbers whose square is less than 2. It's like, but you ask it what number it is, it's like, I don't know. It's just like it just exists by completeness of the real numbers. It's not these things are not computer algebra packages. They don't do calculation. I mean, you have to make them do calculations. They don't do them automatically. And Yale is an undergraduate, and he's formalizing another paper that came out late last year about subsets of the natural numbers with no 3-term arithmetic progressions. How fast can they grow? So there were some breakthrough new bounds in 2022, and then Bloom rewrote the paper was hard to read or something, I don't know. But it was rewritten by Bloom and somebody else. They wrote some survey article. They tidied up the proofs, and now this And now this survey article is being formalised. And again, it's not quite done, but it's not the end of the summer yet. Term doesn't start in the UK till October. And they both look to me like they're on course to finish these things. And both of these results were like featured in Quanta. These were regarded they're not just random results in combinatorics. They're sort of serious results that have answered hard problems. That's an area where we're actually at the point. So here's a question that was, when I was going around 5 years ago getting excited about this, like people would say, well, do you think journals are going to sort of start banning traditional proofs and sort of demanding that every paper comes with a formalization in a computer proof assistant? And like a few years ago, I would say, no, we're a long way from seeing that happen, right? But actually, now I'm beginning to realize that actually in some areas of mathematics, we are seeing that happen. And it wouldn't surprise me if at some point in the future, some combinatorics journal said, okay, we don't want to use referees anymore. You submit your paper, we want to see a formalized proof using a theorem prover. And that would be interesting. I don't know if that will happen, but what I'm saying is it wouldn't be unreasonable for it to happen now, because we're getting a pile of evidence that this is actually a possible. These are single author projects that are running over 3 months, right? They're not 12 author projects that were running over 6 years, like was happening 15 years ago. But I should say that in my area of mathematics, the p-adic language philosophy, we still can't even state the questions. You take a modern paper in the p-adic language philosophy, we haven't even yet got to you need the definitions to state the theorems, and you can't prove the theorems until you've stated them. And so there are some areas of maths where we still have a huge amount of work to do. So here's a reason. This is a bad reason. This is a bad justification. I just mentioned this. This is a justification that's been used by computer scientists for many years, and this is that mathematicians are not very accurate. And our system for checking proofs is lousy, and there's these things like, is the classification of finite simple groups done? And people say it's done, but where's the proof? It's not in the literature yet. And what about Mochizuki and the ABC conjecture? Like, what is going on? Like, you need to get your act straight. The mathematicians make mistakes, and so obviously we just shouldn't trust mathematics at all. And we should only use theorem provers. This is their argument, but that's a terrible argument, right? Because we've got a system that looks for errors, and the system works basically 99.9% of the time. The system works fine.
You say it's a terrible argument, but it's an argument that I remember you making vociferously.
Yeah, it's not. I don't buy. That was when I was having my midlife crisis. So I didn't talk about this, but one of the reasons I got into this was because I was very concerned that some papers in number theory, I couldn't understand them, and I thought, well, maybe they're wrong. And I wondered whether this software could be used to fix them, but as I just mentioned, right now we're still not at the point where I can state those theorems in those articles that were concerning me at the time. So I no longer think you're dead right, David, but I no longer think this is a reasonable way of justifying. I mean, Mochizuki is not going to work anyway, right? The problem with the Mochizuki paper is that he states some corollary, and he says that the proof is that this follows from the 300 pages that we've just gone through, and a lot of people can't understand why that corollary follows. So you can't just sit. You have to know. I knew the proof that a composite of surjective functions was surjective. I don't know if that was obvious to you. I wasn't sort of making that proof. I knew the proof already, and I was translating it. And so the problem is here is if you don't understand the maths, then you can't translate the argument into a computer programming language. So maybe things will get better one day, but we're not there yet. I've got to stop. So I'll tell this story tomorrow, but let me summarize. Let me summarize it now. Scholze raised the following question in 2020. He'd been working in this new area of condensed mathematics, and he raised the following question. There was to to get his theory to apply to the real numbers, he needed to prove some very technical lemma whose proof didn't look much fun. It was a it was a messy technical lemma with a sort of concrete corollary about X groups. And Scholze, just out of interest, started asking mathematicians explicitly if they'd read his paper, and then had they carefully checked the proof of this technical lemma. And he found a lot of people that said they'd read the paper, but they'd never checked the proof of this technical lemma. And he began to wonder whether, in fact, maybe no one had read the proof of this technical lemma. And so he asked the formalization community if it was possible to check the results of the theorem prover. And this was the one thing we needed, right? This was the complex theorem about complex objects, which we hadn't had yet. So this was the perfect target. And it took us 19 months, but we confirmed that the answer was yes. And that's what I'm going to talk about tomorrow, and so I think I'll just leave it here. So thank you very much.
Thank you very much. Is that working?
Flinger.
Okay, so are there questions?
Hello.
Hello.
Thank you for the presentation. Has anyone trained a large language model on lean code base?
Yeah, that's the bit that I didn't get to because I ran out of time. So I'm not going to... let's find... There we go, there's one. So that's a large language model. So as you seem to know already, you don't just have to train large language models on human language, you can train them on computer code. So you can train a large language. This is Facebook's Llama model, and they trained it on lean code, and then they asked it to prove lots of questions, and it couldn't prove most of them. But this one it managed to prove, and this is half of an old IMO problem. So this, wow, right? That one way of interpreting this is like a computer wrote that code. That's like the code I was writing, but it was written by a large language model, and the idea is it writes something and it doesn't work, but the theorem prover just says, no, first error is on line 12. And so then it writes something else. It's like, now first error is on line 4. And then there's some interaction between the large language model and the theorem prover, and eventually the theorem prover says, yeah, okay, this one I believe. And then the large language model stops. So it sort of sounds a bit crazy that idea should work, but it does work. And so you can sell that as a complete breakthrough in large language models and interactive theorem provers, and maybe we're just going to put them together and we're going to get far. But what did it prove? It proved a really easy thing. It proved half of an old IMO problem, but IMO problems were much easier in the 1960s. It proved that 2 to the n plus 1 is never a multiple of 7. So that's a standard undergraduate problem. So large language models can write lean code, but where are we up to right now? We're up to basic undergraduate stuff. And that's where we're up to if they're not right, if they're just writing normal code as well. Yeah, great question, thank you. Sorry I didn't get to it. But yeah, there's clearly some potential, but we just keep never getting beyond. When the computers are in charge, it's just difficult to get beyond basic undergraduate material. That would be the new... If any of these systems somehow started developing harder material by themselves, that would be interesting. But yeah, so that's where we are.
Any other question?
Hi, thanks for the nice talk. As a small report from the computer science side of things, on the question of on the question of requiring formalized proofs for submission. I mean, in computer science we do conferences, not journals, but anyway, even though we have like more than 1 decade, probably we're close to 2 decades at this point of like lots of top research being done in theorem provers, nowhere are they being required yet. So
nowhere? I heard that there was some areas where it was now standard.
I mean, standard and required is not the same thing.
Okay, no.
I mean, there's no formal, like I'm in PL, and yes, they are widespread. Like, I don't know, maybe a quarter, maybe a third, maybe half of the papers have some formalization.
Oh, they do?
But it's not required.
So there you go.
So if that's a predictor, then it'll take a long while until it will be required anywhere in math, I guess.
But I think that if we get to the point where a quarter of mathematical papers are being, in some area, are being formalized, then I think that would be a very interesting development.
Oh yeah, absolutely.
So in some sense, you're way ahead of us. But what
theorem provers were made to do the kind of proofs that we are doing, so it's easier.
And now we're trying to make them do the kind of proofs that we're doing.
Yeah, set theory is hard. So that would actually be my question part of this. So lean is based on type theory, and you touched on this a bit in the beginning, whereas math is usually done in set theory, and then there's this entire mismatch with like classical assumptions and constructive proofs and whatever. So I was wondering, why lean? Like, I mean, there are other theorem provers that actually use set theory as their foundation. Yeah. And so why lean? And was the fact that it's type theory ever a problem?
The fact that it used type theory but not set theory was a minor problem sometimes because we had to work out. So I think even in set theory, we're told lies. Let me give you an example of a lie. It's like the natural numbers are a subset of the integers, right? There's a subset of that's the kind of thing that we would all happily accept without thinking. So in type theory, it turns out that doesn't make sense. You can't even write that. What's happening in type theory? There's a map from the natural numbers to the integers, and there's a map from the integers. There's lots of different 37s. There's the natural number 37 and the integer 37 and the real number 37. They're all, in type theory, they're all different 37s. And in set theory, you kind of think that they're all the same 37, but actually that's not how set theory works at all. Right? In set theory, they're all different 37s as well. It's just that we're very good at covering it up. So there were sort of issues like that. It wasn't actually to do with set theory and type theory. It was just to do with the fact that there's lies in our literature. We're not just using set theory. We're using set theory plus added lies. So one thing we had to do was sort of work out with it. But there was another part of your question that I've now forgotten. That was, great. Yeah, completely arbitrary. I just made an arbitrary choice. But I was an extremely vocal early proponent of the software within the mathematics community, and probably that's the reason that mathematicians are using it now. So it's completely random.
Any other question? Someone in the back. No.
Hey. You said that you can use interactive theorem provers to check code for bugs. Who checks the interactive theorem prover?
You can do that. Well, the problem with checking it, you can't use the interactive theorem prover to check itself by Gödel. But what you can do is you can kind of make sure that the issue, the prover code is gigantic, but bugs in the prover code mostly don't matter. It's just bugs in the kernel that would matter. Bugs in the kernel would let you prove false things. Like if you've got a tactic, this RW tactic, if you've got to prove that x equals y, then this RW rewrite tactic is supposed to change x's to y's. And if it accidentally change an x to something that wasn't a y, then when the kernel ran through it, the kernel would be like, hey, wait a minute, this doesn't follow from the axioms of maths. So a bug in the kernel is a problem, and lean has an incredibly small kernel. And so the idea is you're supposed to read it yourself. But in other theorem provers, they've done other things. In one of the whole provers, they had a sort of a strong version of the prover and a weak version of the prover, and they used the strong version to prove that the weak version was correct. So you can do things like that. But if there's it's not just if there's a bug. You have to find a bug and exploit it to prove something false, right? Maybe there's a bug, but the point is I'm typing in correct mathematics, and so you can't. Here's a better answer. It's better than humans, right? The human literature is full of mistakes, and this stuff here, there's no one's ever pointed out a mistake in Lean's maths library. So it's a lot more accurate. So you have to stop somewhere. So I'll stop there.
Excellent. Next.
So you said that in some areas of maths it's at the cutting edge, like the formalizations in MATLAB.
Well, it can be, yeah.
And in some others it's not. So I guess my question is there some fundamental reason why it hasn't reached there, or just it needs more effort?
Yeah, it's because maths, research level maths, is sort of, it looks like this. Like here's basic undergraduate material, and then research level maths, and then the question is what. Like additive combinatorics is full of lots and lots of really clever ideas. So it's sort of not difficult to trace it back down to the axioms, but somehow number theories existed for centuries. And so there's parts of number theory where it just sort of goes way off and then back down. If you actually look at distance from the things you're doing back down to the axioms of mathematics, it's completely irregular. And all we're doing, and that doesn't mean it's any easier or harder, but it's just this weird, it's just like the stuff at the beginning, right? You want to prove e to the I theta is cos theta plus I sine theta, but defining e to the I theta is incredibly hard. And you don't notice that as a mathematician because it's a completely basic thing. But equivalence relations, you can define them in 3 lines and that's it. Whereas to define e to the I theta, you've got to define Cauchy sequences of rationals. You've got to find the naturals, the integers, the rationals, the reals, the complexes, the theory of infinite sequences. And you, as a mathematician, you just sort of forget. But that's what the landscape actually looks like. And as I say, it's not proportional to difficulty, so it's a sort of a weird new metric. But that's what's going on. It's distance from the axioms. It's a weird metric.
So maybe, like in your opinion, then, if you had loads and loads of undergrad students, you could just reach everywhere.
I think in theory we can reach everywhere.
Fundamental reason.
But in practice, I mean, a lot of this is about social manipulation, right? It's about me convincing undergraduates in particular that it's a good idea for them to spend Thursday evenings hanging out with me, building a maths library. But that's turned out to be something that I was quite good at, it turned out. So that's one of the reasons that the library grew quickly at the beginning, because and now it's all about, now I'm not interested in undergraduates anymore, because we have the undergraduate degree. So now I try and socially manipulate you people, you PhD students and postdocs, because, I showed you, that was the whole point of those, look, here's where we're up to, But, and now you can kind of see, we've got the definition of a Riemannian manifold and no theorems about it. So if anyone wants to have some fun proving some basic theorems about Riemannian manifolds and adding it to our library, but you can't get the undergraduates to do that. So. There's, what? Oh, I'm supposed to advertise. Yeah. Talking of undergraduates, David is going to be running a lean seminar here, right? ETH?
Yes. Thursdays, lunchtimes, so 12 until 2 in the coming semester.
But who are your target?
It's on the course catalog, so...
Who's your target audience?
Bachelor and master students. It's a seminar.
But can PhD students come along and watch? Or?
They can, but we're getting credit.
Oh, I see. Yeah,
so there's at most 15 participants, so if you're the target audience and you're interested, you should make a note of when you can register and do it quickly, because it will probably get taken very quickly. So I think there was one last question here. So this is the last question for today.
Okay, so in computer science, when you want to prove something, the usual technique is to kind of exhaust the number of rules you want to be able to use. So those are your actions, and those are finitely many. And within that bubble, you want to prove things. And if you increase the number of rules you can use, you can prove more complicated things, so on and so forth. Now, in yesterday's talk, you mentioned that one of the problems in mathematics and proving things is that there are infinitely many actions you could do. So, and of course, since you're using lean, you're trying to kind of finitize these actions, the kinds of rules that you can use. So do you think working more on category theory could give us more insights into what kind of actions we can have in the basic kernel for proving algebraic stuff?
I am going to say that I don't think that this software has ever given me that kind of insight at all. Would you say the same? Did it give you any insight in how to do the kind of number theory you knew already? David formalized the statement of the Riemann hypothesis.
You have to know the proof beforehand.
Yeah. We're not doing research I mean, we're doing research, but we're not doing mathematical research. We're doing something weirder. And you have to know what. Yeah, this stuff is not giving us. I mean, that's a proof that a computer came up with. So maybe the computer got some insights from our library, but we're not getting insights from the library. We're doing a tedious mechanical task.
So it's still kind of confusing what would be like a relatively exhaustive, not exhaustive, but an exhaustive enough set of rules that you can use for proving.
Well, I mean, type theory has finitely many axioms,
Yeah.
and so does set. I mean, finally, if you allow a family of axioms, if you count that as one. But you don't prove theorems in mathematics by saying, oh, look, we've got this list of 10 axioms, let's just apply that. Because as well as 10 axioms, you've got 10,000 theorems. And that's how you make progress, you apply the theorems. You see, I mean, induction is an axiom of mathematics. But you know, a lot of these things here, associativity of multiplication, that's not an axiom of mathematics, that's a theorem we proved earlier. You know, and things like Powell-Suck, that says, Powell-Suck will say that x to the n plus 1 is x to the n times x. Right? These aren't axioms of mathematics, these are all theorems. So a lot of the time, and this is a very artificial example anyway, because it was written by a computer. A lot of the time you're not using the axioms at all, you're just choosing things from your very large list of theorems.
Thanks.
Okay. So thank you, everyone. And so there will be a third lecture tomorrow at 5 o'clock about this liquid tensor experiment.
Yeah.